So I don't think I need to motivate you too much, given the title of the workshop itself. I want to compute the endpoint superstring correlator using worldsheet methods and at one loop. And by correlator, that's, I mean, well, this is the full string, open string amplitude. And by the correlator, I mean this part of the amplitude. So you have here the Kobayashi factor that depends on the loop momentum, and then you integrate the loop momentum, and you have the positions of the vertex operators that you integrate, and then you have the Teichmüller parameter, and you integrate over the different topologies of the one loop surface, and you sum over the topologies with overall normalization for each topology. And we want to get the correlators here such that they are BRST invariant. So in the pure spinor formalism, it means that the correlator will be supersymmetric and gauge invariant. And also, we require that it's monodromy invariant, it's single valued, because these are the symmetries of the surface. And I decided to start the talk by the end of it, giving a summary of results. So I will show what's the outcome of the series of papers, and then in the later part of the talk I'm going to show the derivations of why the result looks like it the way it does. So the correlators will be built from kinematic factors written in pure spinor superspace and worldsheet functions at genus 1. At the genus 1 surface. And then what we get is a beautiful Lie polynomial structure for the correlator. That the correlator for endpoints looks like this, where these V's and T's are related to the kinematic factors, and the Z here is the worldsheet function. And these things I will explain later, but you have this combinatoric sum here, and this correlator has a Lie polynomial structure, and I will define what a Lie polynomial is. But it looks very compact, right? You just replace n by the number of particles you want, and the correlator gives you this line here gives you the result. Okay, there are some corrections here, and I don't think I will have time to to explain. One loop. Yeah. What? Open superstring. Type. Yes, it will be SO32. Yes. Type 1. What? Oh, type 1. Oh, massless. Yes. Yeah. So no massive yet. And so that's the outcome of the correlator. And in the process of deriving these, we came across some very nice duality between BRST variations and monodromy variations. So, and well, the BRST operator and monodromy operator, and this is the BRST operator, and we defined the monodromy operator, and this is related to a duality between BRST invariants and generalized elliptic integrants, and I will mention these later. Okay, so if you plug the value n equals 4 in that expression, you will get what Berkovits derived in 2004. That's the expression here. And the kinematic factor is BRST invariant, as he showed in his paper. And the worldsheet functions here are simply 1, and they are monodromy invariant. So that was that's the 4-point amplitude, that's one loop. And then the 5-point correlator, if you expand the permutations there, that's the full answer that you will get. It's very compact, and it depends on these kinematic factors in pure spinor superspace, and they have covariant BRST variations. I will show these later. And these are worldsheet functions. These z's here are worldsheet functions, and the vector index there denotes that it depends also on the loop momentum. And these functions will be built out of the coefficient functions that you see in the Kronecker-Einsenstein series at one loop. So that's how the correlator looks like. I think it reveals a nice structure, and it's compact, and but it's fully supersymmetric. All the gluons and gluinos are there. And let me tell you how you show that 5-point correlator is BRST invariant and single-valued, and there is a strong interplay between doing BRST variations and monodromy variations, which is exemplified in these two lines here. So if you compute the BRST variation of the correlator using the BRST variations of the superspace kinematic factors, you will get this expression here. So you get some overall factor that depends on the kinematics, the polarizations and momenta, and inside the bracket here you get just a function on the surface. And this function here, once you plug their explicit expressions, you can see that they translate to a total derivative. So the BRST variation of the correlator is 0 up to total derivatives on the worldsheet. And now, if you compute the monodromy variation of the same correlator, you get these expressions here, where this omega is just a parameter that specifies which leg you are doing the monodromy variation, and the terms inside the parentheses here are now dependent only on the kinematics. And you can see very clearly in the later parts of the talk that these terms here are BRST exact, so they vanish in the cohomology. So that's the interplay between BRST variations and monodromy variations. And now the 6-point correlator will look like this, and you can start to see that the combinatorics starts to grow, but it is still manageable. But these permutations here are nothing more than just a statement about how to partition the legs among slots here, the words A1 to AR plus 4, and it involves just Stirling set and cycle numbers. They are also called the Stirling numbers of the first and second kind, but I prefer to use the notation Stirling set and cycle numbers.
How do you see the, for instance, 6 points, this should be anomalous for each group, which does not necessarily to
Yeah, so you just that's the slide that will answer your question. So the 6-point correlator is not BRST invariant by itself. If you compute the BRST variation of that correlator that was in the previous slide, and then, well, you need to use the BRST variations of the superfields and all that, you get this answer here where you get a trace over this function there. And it turns out that once you plug the values of the function there, you take the trace, and you use several identities, you can show that this expression here is a total derivative in terms of the moduli parameter. So, well, and you get some anomaly kinematic factor that was known from before. And so the anomaly cancellation happens just like Schwarz and Green knew already in '84, that you get anomaly cancellation after you sum over the topologies and for the group SO32. It's exactly the argument before. Once we arrived here, we stopped thinking about this because this is the same result as in the RNS and in the Green-Schwarz formalism. So now, yes?
You also compute diagrams where you have emissions from both boundaries of the cylinder, and you see the closest string spectrum.
Well, those are things that you can choose by selecting which OPEs you consider, right? So if you put, no, we didn't do that explicitly, but it's just a matter of choosing where to put the particles in the boundaries and selecting which OPEs. Yeah, no, yeah, it's this is general. I mean, you can choose how many particles to put in any boundary you want. Yeah, I'm talking about the monodromies that around the A cycle and the B cycle. So in the torus in the lattice parameterization of the one loop surfaces. So yeah, so these are the monodromies that I will talk about, and I will show that all the functions that we use have no monodromies when you vary them along the A cycles, and then all the monodromy analyses arise when you when you go around the B cycle. Okay. So now it's the part of the derivations. So the formalism that we use is the pure spinor formalism from Berkowitz, and this is how the one loop prescription looks like. You have an insertion of vertex operators that integrate over the surface. You have some picture changing operators and the B ghost. And the vertex operators are written like this. You have this conformal weight 0 vertex and a conformal weight 1 vertex. They are expanded in terms of Superang-Mills superfields. There are 4 types of them. The spinorial potential, the vector potential, and their field strength. And then the procedure here is the standard one. You have you integrate out the non-zero modes from the variables here, and then what you are left with are zero modes, and then there is a prescription to integrate out the zero modes as well. And so when you Okay, so that's A1 there. So when you consider doing these calculations for higher and higher number of points, you will have to be able to do OPEs of many vertices, and that's where the complication arises. One of the complication arises, but I will show in a moment that we have developed techniques to do that in an efficient way, and it involves what we call multi-particle superfields, and they have BRST covariant variations. And then all the complications from the bigos and the picture changing operators are more or less bypassed by completing the expressions that you get from the known parts of the correlators that you get from the known parts of the bigos and using OPEs and all that. And then you complete that expression to something that is BRST invariant and single valued. So, and the claim is that once you do that by brute force or by how can I say that? By some clever ways of finding the completions, then that will be the answer, and that will take into account the parts of the correlator that we didn't know about. So that's the claim. And so I'm now going to talk about these techniques involving multi-particle superfields. So they all start with the single particle description of Berends-Giele theory in 10 dimensions, where this letter I here denotes a single particle label. It could be 1, 2, and so forth. And then this description here is generalized to a multi-particle framework, where now the capital letter B there denotes a word with particle labels. B can be, say, 1, 2, 3, 4, 5, and each of these individual letters denotes a particle. So, for example, when you do the calculations of OPE among vertex operators, you start to see some patterns developing. And so we were inspired by these OPE computations, and we ended up defining superfields recursively like this. So for example, we start with the standard W1 from this superfield there, and then you have multi-particle representatives. So when you have particles 1 and 2, you define the field like this, and similarly for any higher multiplicity superfield word. And the advantage of doing that is that the equations of motion of these multi-particle superfields are very, very nice. And there is no assumption here. This is the result of the calculation using the definitions from before. So this is what you get once you compute the covariant derivative on those superfields. So you see that, well, the first line here was the one that Witten had in his paper. It describes the equation of motion for the spinorial field strength. And now once you go to higher multiplicities, you simply copy and paste the first line here, where now the index is replaced by the word, but then you get some contact term corrections for the equation of motion. And the general structure here is well known. Well, you have to stare these corrections, and then you find the pattern. And the pattern can be described like this, using some deconcatenation of words and the shuffle product. So there is a closed formula for the case of motion for these multiparticle superfields. And I exemplified them with the superfield W, but there are similar equations of motion for all the other classes of superfields, and they all have this nice form where you simply generalize the the terms that were known from before with contact terms.
These superfields are only depend on shell.
Yes. And it turns out that these superfields, they also satisfy a very nice set of symmetries. It's called the Generalized Jacobi symmetry. So, for example, it's manifestly antisymmetric, and when you have three labels there, the labels satisfy the Jacobi identity, and with four you have this identity there, and it generalizes to this expression here, where L there is the linking operator. It's basically the nested commutator. So all the superfields there in KB, where KB can be the spinorial, the vectorial, and so forth. So all the types of superfields, they satisfy these Jacobi symmetries. And you can suspect that by the fact that the superfield satisfy these symmetries, that the BCJ identities will be natural in this framework. But I won't have time to go into this direction, but I just wanted to mention this. And okay, and then the BRST operator in the pure spinor formalism will be simply the multiplication of the pure spinor field by this covariant derivative. So all these nice equations that you saw before, like this, they generalize very nicely to BRST variations. So you can start to think about BRST cohomology identities, and they will come out. They will come up later in the discussion. So it's very important that you have expressions that you can handle efficiently. And then, so for example, when Berkowitz computed the 4-point amplitude, he argued that all the result arose from this contribution from the vertex operators, where you take the zero modes of some variables, and essentially the computation that he did was this one, where you take the zero mode, these combination of zero modes out of the vertex operators, and you get that. And then in this framework of generalizing to multiparticle superfields, you can look at this result and generalize to multiparticle labels. And that's what we did. We simply look at this expression there and generalize it to words. And it turns out that for the 5-point correlator, these are the objects that will come up in the calculation that you can do from first principles. You don't need to assume anything out of the ordinary. So these are, I won't say that these are safe assumptions that you can do. You get these type of generalizations, but there is also a tensorial generalization of these objects, which will involve the loop momentum, But
This is true wherever you insert your vertices. I mean, on the same boundary or different boundaries, you always get the same.
yes, yeah.
This is independent.
Yeah, so yeah, these are the coefficients of the OPE singularity. So that's what I said, that if you take the OPE, for example, to depend on theta 1, the Jacobi theta function, it means that you are in the same boundary. Then if you take the OPE to be theta 4, it means that the states are in the different boundaries and so forth. So yeah, so the coefficient, these kinematic coefficients here are independent on that fact. So I will now talk about the open string correlators, and I just want to recall what a Lie polynomial is. And a Lie polynomial is something that can be written in terms of nested commutators. That's the definition. And there is a theorem that says that if you have an object here that satisfies shuffle symmetries like that, and these t variables are some non-commutative indeterminates, and you sum over all permutations of the words there, then this result here is a Lie polynomial. And just to exemplify the very simplest case is when you have a word of the length 2. If it satisfies shuffle, then it means that this Z12 is antisymmetric. And when you do the sum, you get this nested commutator there. So the theorem is correct. And you can do that for higher multiplicities, and that's what a Lie polynomial is. Okay, so now you have to look at the 3-point correlator that we computed together with Stefan Stieberger in 2011. That's the n-point correlator at 3 level. And if you stare at the correlator that we found back then, and then you rewrite in a suggestive way like this, you will notice that the functions at 3 level that we have in the paper are these ones, and they satisfy the shuffle symmetries. So it's basically what people call a Park-Taylor factor. If you multiply by an additional z p1 to close the cycle, then that's a Park-Taylor factor. But here there is no closing of the cycle, and that means that it doesn't satisfy cyclic symmetry, but it satisfies shuffle symmetry. And then these V's that you see there are simply the pure spinor multiplying the superfield with a word P, and as we saw before, that the word P satisfies generalized Jacobi symmetries that can be written in this form here using the Dinkin bracket. So you see that these blocks there have the same same structure as a Lie polynomial, and that provided us the clue to unlock the expressions for the one-loop correlators. We started by assuming a Lie polynomial structure for the one-loop correlators, and the assumption here is basically because the idea behind this assumption is that the OPEs are a local manifestation of the surface. So if you have some local symmetry at 3 level, we expect we expect the same symmetry to hold at one loop. Because if you are at one loop but looking at the singularities of the functions, then you cannot really distinguish whether you are at one loop, genus 1 or 3 level. So that's the assumption. And we have these kinematic factors satisfying generalized Jacobi symmetries from the OPE analysis that we did before. And then the task becomes, what are these functions here that we require to satisfy shuffle symmetries in the words A, B, and C, and D, and so forth? Okay, so that's the explanation I said before, that the singular behavior of these functions is known from the OPEs, but there is a very different behavior when you compare with tree level, is that the OPEs at the genus 1 surface do not completely fix the functions, because the regular pieces are not fixed by the singularities of the genus. You don't have the analogous of the what's the Liouville theorem. So yeah, computing the OPEs do not fix the functions, but we observe that the requirement of shuffle symmetry for these functions almost completely fixed their non-singular pieces. So that's where that's what I'm going to discuss now, the functions. So this is the A cycle and the B cycle of the torus, and the open string surfaces will be related to the closed string in the usual fashion that they so yeah. Okay, so at one loop, you have this Kronecker-Einsenstein series that magically happens to give us a nice set of functions that we can use to describe what we need in the correlator. So Brown and Levin look at the classical Kronecker-Einstein series from 200 years ago, and then they decided to expand, to do a Lohan expansion like this, and to extract these functions there. So, and if you expand, if you do the calculation and you look at the corresponding functions, you will see that they are nothing more than some derivatives of the log of theta 1, where theta 1 is Jacobi odd theta function. And the notation here that I'm using is this one, where these zi's and zij's are the positions of the vertex operators. So you get an infinite set of functions like that, and you can see that the G with index 1 corresponds to the standard derivative of the log of the prime form, and it's the natural generalization of the tree level 1 over z function. So that's good. And when you look at the higher G functions, you will notice that they have no singularities on the surface. So they're completely regular as z goes to 0. And additionally, if you use the monodromy variations of the theta functions, you will conclude that these Gn functions are single valued around the A cycles, but they have monodromies around the B cycles. Where the B cycle is that one. And then by looking at the expressions, we defined some operator that picks out these monodromy variations of these functions. And the operator looks like this, where these omegas are some dummy variables just to know with respect to which part, which leg we are doing the monodromy variations. So that's the monodromy operator. And additionally, these functions also satisfy a very nice set of identities that are called the Fay identities. And this is an example of an identity like that. You have this combination here that has a singularity, and you have a non-singular piece here, and then when you cyclic symmetrize everything, you get 0. Yeah, well, yeah, it's in, you can look at Fay's book to derive this. Yeah, yeah, well, these are the Fay identities, and you can also argue that the loop momentum will need to vary as you go around the B cycle, but I just don't want to touch too much on this topic there, because to justify this step requires would require much more time. But that's the assumption we do there. Okay, so you can compute the 4 and 5 point amplitudes from first principles, and then you get that, and then you extract the results. Well, you write down the results of those calculations in a Lie polynomial form, and then you extract what is the expressions for these functions that you see there. And that's what you will get. So the vectorial function is simply a loop momentum, and these functions here, they are simply the propagator. It's the derivative of the log of the prime form. So that's what we learn at 4 points and 5 points simply by rewriting the results in a form that we wanted. So, but what about 6 points? And for 6 points, we need a shuffle symmetric completion of the 3-level function that we had in the open in the 3-level correlator, and that's the function we had there. And if you remember, this function here satisfies shuffle symmetries, and then from the singular behavior of these G1 functions, you can argue that this combination here is mapped to this combination of G1s there. They have the same singular behavior, but if you use the Fay symmetries, you will conclude that both of these possibilities satisfy shuffle symmetry. So which one you will need to use at 6 points? And that's where we stood for some time thinking about this, but then we realized that there is a new duality that is present in these manipulations, and this duality will fix will answer this question. And the duality is between BRST invariants and elliptic functions. So I didn't say anything about BRST invariants, so I will do that now. Similarly, as before, we have these 4 classes of superfields, but now we dress the local versions that we had before with kinematic poles that you can look from a planar binary tree expansion like that. So, for example, for each superfield here, you do this. For example, for when you have 3 labels there, that's the sum that you need to consider, and then that defines these calligraphic superfields. And now, because you are dividing by these poles, and the BRST variation of the local versions of the superfields had contact terms, you can do the calculation, and you see that magically the contact terms cancel precisely the propagators from the combinations there, and then the equation of motion that we had before translates to this simpler equation of motion where I don't have contact terms there, and you simply have a deconcatenation of the word there. So, and by historic reasons, we noted these superfields here, the Berends-Giele supercurrents, and you can also show very explicitly that when you define the superfields like these, they turn out to satisfy shuffle symmetries. And that's a mathematical statement. There is no assumption there. It simply happens. So now, since you have objects with nice BRST variations, you can start to simply follow a mathematical route and start to define things in such a way that you get a nice BRST variation for the objects that you define. That in some sense you get BRST covariant expressions. So for example, if you define an object like this and similarly like that, you see that the BRST variations are very simple, and it involves just a deconcatenation of the words there, and you get a minus sign there. So because of this minus sign, then you can start to ask if you can construct some linear combinations such that the BRST variation will annihilate the whole thing. And it turns out that you can do that. There is a very beautiful combinatoric generation formula for this that satisfies this quest of defining objects that are BRST invariant. And the simplest example is this one, and then you have a 3-term sum for the 5-point BRST invariant, and we have a general formula that simply involves some combinatorics, and it's very beautiful. It involves shuffle products and linking operators and all that. So it's a nice object, and we also have generalizations for arbitrary tensor ranks. So this is a scalar case, but you can also consider vectorial extensions like these, where now this the vector index is carried by momenta, and you also have some definitions there, but I just want to say that this can be done. And in the end, after you go through all these definitions, you will see that these BRST invariants satisfy very nice cohomology identities. So for example, if you contract the vectorial BRST invariant with a momentum, and you sum this combination of scalar BRST invariants, you get 0. And that's a statement in the cohomology. So these expressions here turn out to be BRST exact. And you also have identities that involve what we call the change of basis, where, for example, here the basis involves the first letter there being 2, but you can rewrite it as objects that start with the letter 1. And these are the type of objects that you get. And I won't be able to touch the subject anymore, but there is a very, very nice mathematical structure behind these. These identities here are not random, and they have a deeper meaning. Oh, yeah, I can do that. I'm sorry. When? Okay. Okay, sorry. Okay. Yeah. Okay, so the idea now is to derive the worldsheet functions by mimicking what we know from the BRST invariants, and mimicking the behavior for these worldsheet functions. So, for example, you can show that from the functions that you had before, if you do this sum here, which corresponds precisely to the BRST invariant that I showed you before, the result is single-valued. And that is a very strong indication that something is going on there. And we have several identities. Basically, everything that you can do for the BRST invariant side, if you do the same for the elliptic, for the worldsheet function side, you get this mapping here. That there is a new duality at play there. And of course, we have tensorial generalizations. So this is why the papers are long, because you need to define these things and show that they are satisfied. But in the end, if you mimic what you saw at for the vectorial BRST invariant and construct a vectorial function, you see that it's single-valued. So everything is working in the same way, and you can also check that the same BRST cohomology identities that you had before are translated to identities among these functions. So this is very surprising, because on the one side you have polarizations and momenta that satisfy some homology identity, and on the other side you have functions on the surface. So they know only about the z positions and the tau parameter, and they happen to satisfy exactly the same identities, and that is very surprising to me, at least. And it turns out that you can exploit this duality even more, because you can now derive what the functions should be by requiring that the monodromy variations of the functions are mapped back to what we already know at the BRST invariant level. So, for example, if you require the monodromy variation of the 6-point function that I said before, and write it like this, just mimicking what you know before, what we knew before, you get that there is a unique solution for what should be used in the 6-point correlator. And similarly, you can do that for everything else with vector tensors, and you can fill up everything like this. And so this is the last slide. So the correction terms that I mentioned in the first slide, they involve some other types of superfields that we called refined and anomalous, that they are related to doing BRST variations and getting the anomaly out, or the anomaly cancellation out. And this is what you get when you have these refined superfields. they increase this degree that we have here. So everything that I said up to now involves fields that we call degree 0 of refinement, and then the expression generalizes to this sum over different refined superfields, and then you have some anomalous contribution there. And when you do this, and when you check these at 7 points, you will get a BRST invariant and single value correlator. But once you plug all the expressions here for 8 points, you will see that the BRST variation does not vanish, and what remains is simply the holomorphic modular form, G4, the Eisenstein series. So everything complicated that needed to cancel cancels. So everything that has a singularity on the surface and all that is gone in the BRST variation. But there are still some terms here that are, well, they are single valued and they don't have poles that survive in that computation, and it turns out that it's a bit complicated to get rid of these terms, but they have a nice structure, let me say that it just doesn't seem like it's a completely random mass. There is a very nice structure to what remains, and I believe that there are some other types of superfields that maybe we missed, and when we add those, these will cancel, and that's at 8 points. And I believe that once this issue with remaining Eisenstein series is solved, then we will get the endpoint correlator for free. I believe that solving the 8 points will solve the structure for endpoints as well, but that's still work in progress, and well, it's a lot of work, so it's taking some time. So thank you.
Besides anomalies, the other issue that Michael and I looked at 35 years ago was the cancellation of divergences between the annulus and the medius strip.
Yeah.
Did you look into that?
Yeah, it's exactly the same thing. It will cancel for SO32.
Well, that was our conclusion, but we felt that our reasoning wasn't very rigorous because you have to regulate both of them, and it was unclear how to relate the regulator of the one to the regulator of the other.
Well, but if you compute the correct correlator, then it's the correct answer, so that there is no divergence. And yeah. Yes. So it's exactly the same thing. When we sum over the different topologies here, we will get the cancellation. Well, no, you have to integrate the loop momentum just like Dock and Fong. But that's the usual prescription to integrate of the loop momentum, and then you get single valued expressions, and yeah. But I mean, all I can say is that if you get the correct correlator, everything will work out. I mean, and yeah. So. Oh, but by the way, there is one paper from a Japanese author called Tsukiya from the 80s, where he simply wrote down expressions for correlators up to 8 points, and just for the bosonic states. And when we compared our correlator with his correlators, they match. So, well, we compared up to 6 points, and they match. So, I believe that we have the correct correlators at hand.